Okay, so thank you for inviting me. And some of you must have seen this talk before or variations, but I mean, this is my best work, so I thought that this is the right thing to present at this conference. Let me start with what is a semi-definite program. As we know, the semi-definite program is defined by a bunch of symmetric matrices. So the AIs are symmetric matrices. Does this work? Yeah, okay. So the AIs are symmetric matrices. B is a symmetric matrix, and we have xi scalar variables, and we want to optimize a linear objective function, so supremum C transpose X, and the inequality is a linear matrix inequality. So what that means is that if A curly less or equal than B, means that B minus A is positive semi-definite. And everything is symmetric, of course. So this constraint means that the B minus some xiai is positive semi-definite. And an n by n matrix Y is positive semi-definite, symmetric, everything is symmetric here, if the principal subdeterminants are non-negative. So I take the principal subdeterminants and those have to be non-negative. Alternative definition is if I take this quadratic form, V transpose YV, that's non-negative for every V vector. So this is a semi-definite program. Now, why do we study semi-definite programs? Well, just a very quick overview of that because there's not much time for that. So first, it has a lot of applications. Second, there is beautiful theory in many areas. So for example, there is beautiful theory in duality, interior point methods. One can generalize interior point methods from linear programming and geometry. Now, just to show a little bit of a motivating picture, we can draw beautiful pictures of semi-definite programs. So for example, this picture on the right, that's the set of 2 by 2 positive semi-definite matrices, which can be nicely pictured because of symmetry. So there is only 3 dimensions that we have to picture. And this is the feasible set of under nice SDP. Of course, we have to take the convex hull of the surface because everything is convex. So, and there are some very interesting glitches, which is what got me excited. So for example, interior point methods is very well known. Generalizing them from linear programming is not an easy thing to do, right? So, and duality theory also doesn't work as well, and that's what got me interested in this subject. So I'm going to talk about duality theory of semi-definite programs. So duality, well, we can take this SDP, which is a maximization problem or supremum problem, supremum of a linear objective subject to that linear matrix inequality, right? And it has a dual. Now, the dual is that we have a Y positive semi-definite variable matrix, and we have a bunch of linear equations. So the dot product of matrices is essentially, we stretch them out as vectors, and then we take the inner product of those vectors. So we have a bunch of linear equations, and then we have a linear objective function, infimum of B dot Y. And what's easy is that if X and Y are feasible, then the C transpose X is less or equal than the B dot Y. So that's just like linear programming. Nothing is different from linear programming as far as that goes. Now, ideally, of course, we would like to have an X star and a Y star for which the objective values are equal, right? Because if that happens, then we proved optimality, right? Then that's a certificate of optimality. Now, that's where things diverge from what we are used to in linear programming, because SDPs can be pathological. So, for example, they may not attain their optimal values, or there could be a positive gap, meaning that the objective value of one could be 1 and of the other one could be 2, which is bad, right? And I'm a little bit paraphrasing here things, so one can say that, well, is there something wrong with SDP duality? And the answer is yes. So this is the basic setup. So I'm going to show a bunch of very basic examples, which show up in every textbook or survey, pretty much. So let's take this one variable SDP. So x1 is the only variable. We want to supremize 2x1 subject to that linear matrix inequality. Now, I put everything on one side, right? So I rearrange things so it looks like that, right? The question is, what is the x1 that makes that matrix positive semi-definite? Well, there's only one x1, right? Because the determinant of that matrix is negative x1 squared, right? So the only feasible x1 is x1 equal to 0, right? So the primal has optimal value equal to 0, obviously. Now the dual, that takes a little bit of that's like a one-line computation. So dual is, this is the matrix, this is the dual matrix. The off-diagonal elements are 1, and then these are free. And I want to make the y11 as small as possible, right? So what can I make the y11 so that that matrix is positive semi-definite? Well, I can make the y11 to be a tiny small positive number, but I can never make it equal to 0, right? So this can never be 0 because the off-diagonal element is 1, and in a PSD matrix that cannot happen. So the dual has an unattained 0 optimal value. So that's really an infimum, not a minimum, right? Now, there's a nice picture associated with it, which I would like to show. It's not about the mathematics, but it's a nice picture. So what does the primal do? The primal is looking for the largest 2x1 or x1 subject to negative x1 squared greater or equal than 0, right? So what is that? It's like we have a downward parabola, and then we are looking for a non-negative number on it, right? And there's only one such point, right? So the x1 equal to 0. So we're looking at a degenerate parabola. That's the primal, right? Then the dual, but the dual is very familiar, of course, because we have a y11 and a y22, which are non-negative individually. And the product has to be greater or equal than 1. And we are looking for the smallest y11. So that's obviously, we are looking for the leftmost point on a hyperbola, and we know that doesn't exist, right? So this is a nice dichotomy between the conic sections. So SDP has to do with conic sections. So that's the first pathology, an unattained value. The other one, it's a bit more complicated. So in this particular instance, I can see that the x2 always has to be equal to 0 for a similar reason as we have seen before. If I package everything on one side, then I see that the x2 is associated with an off-diagonal non-zero element, but the diagonal element is 0. So the x2 always has to be equal to 0, right? So that we can figure out. But the dual has an optimum value which is attained. That takes like a little bit of a computation, so I'm not going to show every detail, but one can figure that out. So there's a positive gap. So far, these are the two examples. So I should stop here for a second and see if there is a question. So we have two examples, one unattained dual value, in the other one we had a positive duality gap. So now we would like to somehow define precisely what we mean by bad behavior, right? So I'm going to look at the semi-definite system, and I would like to see when that system is badly behaved. And the reason I'm looking at the system is because in one instance I had an unattained dual value, in another one had a positive gap, so those are obviously not the same thing, right? So I'm going to say that this system is badly behaved if there exists an objective function for which the primal is finite, but the dual doesn't have a solution with the same value. Now that breaks down as either the dual doesn't attain, or there is a positive gap, or maybe even both, actually, right? So that's the definition of bad behavior for us, and well-behaved otherwise. And what is a slack? Now, that's the only definition that I'm going to need. A slack is a positive semi-definite matrix, which is a B minus some xiai. So that's a slack that takes up the slack between the right-hand side and the left-hand side, just like in linear programming. And that's the only definition that I'm going to need, and we can already state a theorem about this. So the theorem is, okay, sorry, it's not yet. So the motivation is that, so these instances, they show up in lots of surveys and textbooks. So if I look at these two systems, right, and if I stare at them for a while, then I can see that somehow they look similar, right? So there is some strange similarity. And what is the strange similarity? Well, in both of them, well, this doesn't quite work, but anyway, so we can see that the right-hand side is this small identity and then some zeros, right? And on the left-hand side, I see this sort of off-diagonal structure in one of these matrices. There's this off-diagonal or per-diagonal structure in one of the matrices that happens both here and in the first system. So the question is, there is some curious similarity, and it also happens in the other instances that were published in the literature. So then we start wondering, is there a combinatorial structure there? So then the spirit of ACO, came in and then said that, well, maybe there is some combinatorial characterization or something like that here. And then we can state the theorem in a reasonably simple fashion. So there's the semi-definite system. I would like to know if it's well-behaved or badly behaved. And I'm going to assume that the maximum rank slack is of a certain form. Now, firstly, there exists a maximum rank slack because a slack can have rank 0 or 1 or 2 or 3 and so on, right? So there is one which has maximum rank. And I'm going to assume that it's normalized so that it's a small identity and then lots of zeros. I can assume that without loss of generality. And the theorem is that the semi-definite system is badly behaved if and only if there exists a V matrix, which is a linear combination of the AI matrices, which is of this particular form. The particular form means that this V11 is R by R, so that matches the size of the identity in the maximum rank slack. This V22 is positive semi-definite, right? And the range space of this one, this submatrix, is not a subset of the range space of the V22. And that's the complete characterization of pathological behavior, right? So this has to be positive semi-definite, and the range space of this should not be contained in the range space of that. That's the characterization. And just to do a sort of a sanity check that this actually works, so this is our first example, that one variable instance, right? Now what is a slack matrix here? So there is only one slack matrix because the x1 is always 0, right? So the only slack I can have is just this matrix, right? And then, so that's the z, right? So then I'm looking for a v such that this portion is arbitrary, and the range space of this is not subset of the range space of that, and that's the v, right? So we can do this sanity check, and we can immediately see that indeed things are working out. And we can spot these excluded matrices in the published examples, right? I mean, I thought of this terminology excluded matrices because, I mean, this is kind of a little bit like excluded minors. I mean, obviously it's not graph theory, but still the spirit is somehow similar. So I should stop and see if there is any question, maybe. Okay, so what is missing from this theorem? What is missing is that, so if I show you the z and the v, that proves that the system is pathological, it's badly behaved. However, they don't give me a bad C objective function. So they prove that there exists a bad C objective function, but they don't give me a C objective function, which is not entirely satisfactory. And otherwise, it doesn't give me a polynomial time or easy to verify certificate of the bad behavior. What does it mean? So I can show somebody the Z and the V, and I can tell him or her, okay, so please believe me that the system is badly behaved because here is the Z and the V, right? But then this other person could say that, well, why should I believe you? And I could say that, well, because my theorem says so, right? So if you read my theorem, then you should be convinced. But the theorem is long and maybe boring, so maybe that person doesn't want to read it, right? So the idea is that, so here's an aside. How do I prove to somebody that a linear system of equations is infeasible? The way to prove it is I show the row echelon form. So I bring it into row echelon form, which has an equation which says 0 is equal to 1, and that, of course, it's convincing that the original system has to be infeasible. So I'm going to borrow ideas from the row echelon form. And for that, I'm going to reformulate this system. And I'm going to do a bunch of operations which obviously keep it in the same behavior as it was before. So the first one, I can apply a rotation to a matrix. So I can apply a similarity transformation to all AI and B. That doesn't change the behavior. The second, I can translate the right-hand side. I can replace the B by the B plus summation AI BI. I can do a transformation on the AIs. I can replace an AI with a combination of the AJs, and I make sure that the lambda is non-zero, just to make sure that this operation is reversible. And I can switch an AI and the AJ, right? So these are all the operations I can do, and these obviously are not going to change the behavior of the system, because these are reversible, and then of course translating the right-hand side doesn't do anything. So these are just essentially elementary row operations done on the dual, right? So, I mean, I can switch two equations in the dual. That doesn't do anything bad or good. And then here's the next theorem. The system is badly behaved if and only if it has a reformulation of a certain shape. And there is three things to absorb there, so it's not too much. It's more complicated than the previous theorem. So the three things to absorb is that the Z is the maximum rank slack. So I made that to the right hand, made that to be the right-hand side. I can always do that, right? The second is that these GI-HI matrices are linearly independent, meaning if I take a linear combinations of those matrices and it turns out to be 0, then the coefficient set to be 0. And the HM, that lower corner, has to be positive semi-definite, right? So how do I get this? Now, how do I get from a bunch of matrices, how do I select some of them in which a certain block is linearly independent, and how do I make sure that the corresponding blocks in the others are 0? Well, the way I do it is basically Gaussian elimination, right? I mean, I imagine that, so I make these AIs into vectors, right? Long vectors, and I do Gaussian elimination so that these rows are linearly independent and the others are zeros, right? I mean, that's just Gaussian elimination. And so this is an if and only if characterization. And I mean, I'm not going to go through the steps here, but it's really kind of like a paragraph in the paper. So if X is feasible, then I can show that because of that linear independence condition, that the xk plus 1 through xm are all 0. So those are identically 0 variables. Therefore, if I take the supremum of negative xm, that's going to be 0, right? So that's an objective function which gives me a 0 optimal value. But there is no dual solution with value 0, right? So, I mean, this needs a little bit of a work, but the point is that this trivial objective function, supremum of negative xm, is a bad objective function. So from this reformulated bad system, it's easy to read off a bad objective function. So here's like a trivial example, like a one variable example. So this system is badly behaved, right? But how can we tell? I mean, I only have to try two objective functions, x1 and negative x1, right? It's actually a good exercise in linear algebra to try to figure out whether this is well behaved or badly behaved. It's not, I mean, it takes like a half page to figure it out. But on the other hand, if I reformulate it, I get back that original system, which is trivially badly behaved, right? So it's not, so actually reformulation does make life simple even in a one variable case. Now a larger example, which is admittedly artificial, 4x4 matrices, 4 variables. How do I tell if it's well behaved or badly behaved? It's basically impossible, right? Because it's just kind of hopeless. But on the other hand, if I reformulate it, I get this system in which the matrices are sparser, but that's not the main point. but I can see easily that x3 and x4 are 0, so therefore the supremum negative x4 is 0, and then there is no dual solution which has optimal value 0. So reformulations do help. So some corollaries. So for well-behaved systems, I can create a similar reformulation. I'm not going to go through the steps. So this question, if I ask this, is this system badly behaved or well-behaved? That's in NP intersect co-NP in the real number model of computing, which is essentially that I can write down square root 2 and square root of 5 in 1 unit of space, and I can add them in 1 unit of time. This is liked a lot by numerical analysts, not so much by computer scientists, but this is a well-accepted model of computation. And the certificate, well, I reformulate it. From the reformulation, it's trivial to see that it's well-behaved or badly behaved. And then I have to convince you that that's indeed a reformulation. So I have to provide the transformation, and I have to provide a proof that the Z is in the maximum rank slack. So that I kind of didn't talk about that. 2 minutes, okay. So a proof is, I'm not going to show that. So there's 3 papers. So I've been working on this for some time. There is a paper which was quite theoretical, the closedness on the linear image of a closed convex cone at 2007. And there's a paper in Science Journal of Optimization, that semi-definite programs, they all look the same. And then finally, this one, which I just essentially presented, that's a version that really boils it down to a proof which is mostly just linear algebra, and there's a little bit of convex analysis in it. So, and then in a similar vein, there is a bunch of other papers, which, I mean, if you're interested, you can see them on my webpage. So I want to thank you for your attention.
We have time for a couple of questions.
So my question is about, you define badly behaved if you are given the A's and the B, right? So if you are given the matrices and the right-hand side, and then badly behaved means that there exists some pathological C. So I guess 2 questions. My 2 thoughts are related to, well, you could then think about variants of that, where can you characterize what a triple, A's, B, and C, that are fixed, when that is badly behaved?
Yeah, that's a good
question, right? And the other question is, well, what if you then leave B and C free, and you fix A, and can you ask, okay, whenever I plug B and C, this is going to be well behaved? And maybe one of those 2 questions is trivial, or maybe, I don't know, have you thought about those?
Yeah. I mean, the first one is, for example, it's very interesting to look into when there is a positive duality gap, right? So I have a paper in which I completely characterize the case when there is 2 variables. So, which is, I mean, it's not much to write home about, but it's a start, hopefully. So that's a pretty hard question, actually. So to figure out a complete characterization. For positive gap, for m equal to 2, I can do it, and then hopefully one can do more. So the other is when you fix the AIs and you vary the B and the C. That's a good question that I haven't thought about, actually. That one I don't know. Yeah. Yes, done.
Suppose somebody gives you an SDP. Is there some simple recipe I can follow to perturb it in some minimal way so that it's guaranteed to be well behaved? There's no duality.
Oh yeah, I mean, SDPs which satisfy Slater's condition, those are well behaved, right? So we can always perturb SDPs to make them well behaved. But the issue is that if you take a bad problem and you perturb it, you get a good problem which is awfully badly conditioned. So that there's a trivial perturbation. Just add epsilon times identity to the right-hand side. I mean, that's going to fix things, but it's not really going to fix things. So
I guess if you perturb it a little and it becomes well behaved, then there's no duality gap. But then possibly either the primal of the dual will change a lot in value, right?
Yeah. So I mean, like perturbing a bad problem makes it good, but it still doesn't make it good because it's going to be awfully badly conditioned. I mean, just like an infeasible linear system of equations, we can perturb it, but it's not going to be very nice once we did that, yeah?
Well, if there are no further questions at this point,